Hello everyone. I record this video in internet cafe because something wrong with my computer and my hometown have really bad internet. I can't do the work. Um, so so let's start. My topic is learning to count objects in image. My goal is to basically accurately estimate the number of individuals in the image, including the number of people, the number of cells or vehicles. For the method, I take a supervised learning approach to this problem, and so require a set of training images with annotation. The question is what level of annotation is required. Arguably, the bare minimum of annotation is to provide the overall count of objects in each training image. Okay, this is a true image with a lot of blue points. We are noted each point with this sign. So our task is to count the number of sun in the image, and this is a true image on the street. We can see each people as a blue point, like the blue point in this image, and we use the same way to notice each people with this sign. And we count this sign, we can get the true. We can estimate the people, how many people on the street. Okay, this is my training site. The left one is like this image, blue point image, and the right one is a black image and with a true number of the point of the point in the left image. So our task is to use MATLAB to estimate the number of point in the left image and compare with the true number of point in the right image. So we can train the supervised learning. What technology I used, I invented the hard task of learning to detect and localize the individual object instance. Instead, I case the problem as that of estimating a continuous density function whose integral over any image region gives the count of objects within that region. We start with a set of dot annotated training image and a set of features so that each picture in those images is assigned a real valued feature vector describing the local appearance. In my experience, this feature was defined either using shift-based visual dictionaries or a set of randomized trees. My system then learned a linear mapping that transformed the feature vector at each picture to a density value, obtain density function value in that picture. So during the training, I optimize the coefficients of that linear mapping so that the density function resulted from the mapping matches the group truth density functions defined as a sum of Gaussian kernels centered at the user provided dots as closely as possible. Additionally, we imposed a quadrant regularization on the mapping coefficient to prevent overfitting. Okay, next, I use the method distance to count to use in the counting task. This is the function of missing distance. Really, I use for in my task. The missing destiny is particularly suited for the learning to count problems, as it implicitly corresponds to learning from a combinatorial number of sub-images. Furthermore, the missing distance can be computed very efficiently using any of 2D maximum subarray algorithms. This is my experience result. In this frame, the true point is equal to 266, and we use the MATLAB to estimate the point equal to 265.79. The same way the other picture. We can see basically it's accurately. Okay, it's an application of this of my experience. We can count the people, how many people on the street. Okay, that's my references. Use this paper. Thank you.